continue with the lecture. I left you with this equation, this formula for the entropy. So this formula is the general formula to measure the change of entropy. So we can use this formula also to calculate the entropy change when shock wave happen. So what we can do is we put in the value of this constant, the Cp and R, and also we need to know what is the temperature before and after the shock, and also the pressure before and after the shock. And after that, we can calculate this to get the entropy change. So the second law of thermodynamics requires that the entropy increase across the shock wave. So that's the law. A shock wave, therefore, a shock wave cannot exist for values of Mach number less than unity. Entropy change would be negative. So what does it mean? If you look at this diagram, this is the line made by this formula. So if you look at here, when Mach number is equal to 1 and lower, the change of entropy will be negative, which is lower than 0. So according to this law, this is not possible. Therefore, the only possible thing to happen is the entropy will increase after shock wave. So we need to bear that in mind, that the entropy will always increase after shock wave. Okay, now we go to example. So this is the example that we want to learn, example 12.8. So actually this example is related to example 12.6, but never mind. Let's read it. If the air flowing through the diverging nozzle, remember, converging and diverging nozzle of example 12.6 experience a normal shock wave at the nozzle exit plane. So at the diverging nozzle, shock happen. So we can look at the figure 12.30 later on. So determine the following after the shock. A, the stagnation pressure, static temperature, static density. B, the entropy change across the shock. C, the exit velocity. D, the mass flow rate through the nozzle. So we use the constant K equal to 1.4. So what is in figure 12.30? So this is the figure. So from example 5.6, this is the outcome at the condition at location 1, and we want to know what is the value for this parameter at position 2 after the shock wave. Alright, so we go back to the equation, the question, and how to solve it. We go to the solution. So we have some assumption at the top, and we also have the constant of the ideal gas. So we do some analysis. A, the fluid properties at the exit of the nozzle just before the shock are evaluated in example 12.6. This is similar with in the diagram just now. So this is the value. And now, how to calculate the value of pressure, temperature, density, etc. after the shock is we use table A14. Table A14. And that is for Mach number 1 at position 1 equal to 2. Alright. So what is table A14? We go to this table. Okay, this is a table A14. If you have the book, the channel book, it's in the appendix. So we go to 2 right here, and we can get the Mach number 2 is equal to this. See, if you look at here, when the Mach number is high, the output of the Mach number is low, become lower. The higher the Mach number, the lower the output Mach number. Okay, so and we can also have the ratio for pressure, density, temperature, stagnation pressure, and this is the stagnation pressure over the initial pressure. Okay, we look at this value and we compare to the solution right here. So it's similar. See, Mach number is 0.5, lower compared to the previous one, 2.0. So we use this value to calculate the condition, the value at after the shock. So the value that we get is stagnation pressure equal to this. We get value also for the pressure at location 2, temperature, and also density. Alright, so just bear in mind that value. And again, we have this equation to solve the entropy change. So since we have this value already, we just put in the value into this equation, and we can get the entropy change, and it is a positive value. So it is according to the law of thermodynamics. Alright, and afterward, in question C, we need to the air velocity after the shock is determined from this equation, where C2 is the speed of sound at the exit condition after the shock. Okay, you need to know the speed of sound is not always the same. If the temperature is if you use this equation, if you look at here, the temperature is changing, so therefore the speed of sound is changing. So you need to use this formula to calculate the new speed of sound. So after we put all the values inside, we can get the air velocity V2. So previously we don't get the velocity, and afterward we can get the velocity after we know the temperature and also the Mach number. And finally, the last question is the mass flow rate through the nozzle, D. So how to solve that is, the mass flow rate through a nozzle, through a converging and diverging nozzle with sonic condition at the throat is not affected by the presence of shock wave in the nozzle. Therefore, the mass flow rate in this case is the same as the determined in example 12.6. So it's not changing, it's the same. Okay, we finish with the example.